QR codes. Whether you use them to share links, photos, or rickrolls, it seems like QR codes can instantly turn a bunch of random squares into a portal to almost anything online. Surprisingly, every single one of those squares has its own purpose. And in this video, I will show you the genius design behind the QR code. Before we start, it is important that we know that there are 40 sizes or versions of QR codes that range from 21 by 21 to 177 by 177 squares. Each version can hold a certain amount of data, and the larger they are, the more information their message holds. Nearly every QR code is composed of black squares and white squares. The white squares represent a 0, and the black squares represent a 1. When these squares are put together and scanned, these ones and zeros will form a message in binary. We'll come back to this later. Regardless of their size or type, every QR code has a couple things that remain the same. In this video, I will be using the smallest version of QR code for simplicity, which is 21 pixels by 21 pixels. The most recognizable part of a QR code are the 3 big squares in the corner. These are called position squares, and they help the scanner figure out the orientation of the code. For example, if you scan a QR code upside down, the position squares will tell the scanner how the code is positioned and will read it accordingly. You may have also noticed a smaller square closer to the center. These squares are called alignment patterns. Whenever a QR code is distorted or at an angle, the scanner will look for an alignment square and use it to rescale the QR code back into a square. Depending on the QR code's size, it may have multiple alignment squares or none. Together, these squares will help the scanner read the code no matter where it is. In between the 3 position squares are sets of alternating squares known as timing patterns. These patterns act as a ruler, and they help the scanner tell what version or size the QR code is. For example, a version 1 code has 5 alternating squares, while a version 2 has 9. For each version of QR code, the timing patterns will increase by 4. Finally, there are sections of the QR code that are set aside to help format it. These will be useful once we fill out the rest of our code. Now that we've got these squares in place, all that we need to do now is fill in the rest of the code with data. Before we start to fill in the data, it is important to know how the scanner reads the code. When reading the data, the scanner will start in the bottom right corner and alternate upwards, and will continue this pattern while snaking up and down the rest of the data. No matter what size a QR code is, the scanner will always follow this pattern. In the bottom right, the first thing the scanner reads are these 4 squares, or bits. These bits will tell how the data is formatted. If the scanner reads 0001, it'll be numeric and only have numbers. If it reads 0010, it'll be alphanumeric, which includes numbers, capital letters, and symbols. 0100 will be binary, which is in bytes, and 1000 will be kanji, which is in Japanese characters. Our QR code will be using binary for its message. Once the scanner reads how data is formatted, it will read the next 8 bits. Each set of 8 bits is called a byte, and this first byte will help the scanner know how long the QR code's message is. In our QR code, the message is 11 characters long, which is 00001011 in binary. To show the scanner that the message is 11 characters long, we will add these 8 numbers to our data. Now that we've specified the data format and the message length, we can now write out our message. In our message, each byte will represent 1 character. Let's start with the first character, S. To add it to the QR code, we will have to translate S into binary, which is 01010011. Once we have the letter in binary, we will then place these 1s and 0s into the code. Now, when the scanner reads this byte, it can translate it to the letter S. This process will then repeat for each character in the message. Finally, once the message is written out, 4 white squares, or zeros, will be placed at the end of the message to tell the scanner that it is complete. Even though our message is complete, there are still 13 bytes of empty space in our code. This data will be filled with redundant information called Reed Solomon Error Correction. In case you accidentally rip your QR code or spill your favorite drink on it, this redundant data will make the code readable. A QR code can have 4 levels of error correction, and its level is displayed in the format strip. It can either have low, which is 7% redundancy, medium, which is 15% redundancy, quartile, which is 25% redundancy, and high, which is 30% redundancy. A QR code with high error correction can still function with 30% of it missing. However, higher levels of error correction reduce the space available for the actual message. For our QR code, we'll use 25% redundancy. Now that all of our data is filled out, we only have one more step until we have a working QR code. You may notice that it doesn't quite look like a normal QR code yet. This is because there are still huge sections of black and white squares present. Having large sections like this may confuse the scanner and lead to the code being read wrong. In order to prevent this from happening, QR codes have 8 unique masking patterns, and the type of mask is specified in the formatting strip. These masking patterns are almost like filters that are added to QR codes to make it easier for them to be read. There are 8 different masking patterns because some masks work better than others. To find the best possible mask, all 8 of them are tested, and the one that evenly distributes the squares the best is selected. For our QR code, mask 0 is the best option. To add this mask, we will only put it over the data of our code, and we will flip the color of the highlighted squares. For example, a black square that is affected will turn white, and vice versa. By applying this mask, our QR code is now much easier to read. Now that our formatting strips are complete, you may notice that there are still some empty squares that haven't been filled yet. These places will be filled with redundant formatting information in case the QR code is damaged, similar to error correction. Now, we only have one pixel left. This pixel is the most crucial part of the QR code. Just kidding, it is completely useless, so it will always be colored in black. Finally, most QR codes have an area surrounding it called a quiet zone. This zone isn't completely necessary, but it makes it easier for the scanner to read the code without interference from things surrounding it. Now that everything is accounted for, we now have a working QR code. If you are confused about some things or want to learn more, I will link some resources in the description below. Thanks for watching, and if you enjoyed this video, please consider subscribing.